Hi, welcome. This is lecture number 12 on topology, fourth lecture on closed sets, and we are going to talk about the closure of a subset in a topological space, which we ended the last lecture with. Okay, so let us get started. So let X be a topological space. Okay, A be a subset of X, then we define closure of A, which we denote by A bar, or closure of X, closure of A in X, or closure of A in the space X tau. Okay, this is the definition, the smallest closed set containing A. So what do you want today? You want a concrete description. The closure. So if you had really understood our motivation, how we define the adherent point and various results, okay, about A closed if only if it contains adherent points, etc. Okay, it should not be a surprise. What should, okay, so let B equal to set of all adherent points and points of A. Okay, then I want, my question is B closed? Right? No. Now suppose I prove B is closed. The answer is yes. Notice that every point of A is an adherent point of A. Therefore A is a subset of B, and you also say B is closed. Now if, okay, next you look at A closure. Okay, this we know it exists, therefore A is a subset of this, right? Right? Now what do we know? If X is an adherent point of A, that is X belong to B, then X necessarily belong to A closure. Do you understand this? Okay, this we proved earlier. What did we prove? If X is an adherent point of a set A, and if A is a subset of B, this is nothing to do with this B. Okay, if A is a subset of, let us say, T, then X is an adherent point of T, right? Therefore any adherent point of X in B implies X is an adherent point of A closure also. Since A closure is supposed to be, this one is a closed set, therefore X must be in A closure. So what is that we have concluded? We have concluded B must be a subset of A closure. Okay, and A is already contained in B, right? And we already know B is also closed. Therefore what is the conclusion? A closure is nothing other than B. Do you follow that? Yeah, pause, review, proceed. So we need only show that B is closed. Okay, suppose not. See, now you see how we are going to use our thing. If it's not closed, what does it mean? Some set is not closed, meaning an adherent point of the set is not in that set. Therefore there exists an X in X, so that X is an adherent point of B, but X is not in B. Yeah. If X is not in B, what does it mean? What is B? B is set of adherent points, right? Set of adherent points of A. Therefore X is not in B is same as saying X is not an adherent point of A. Do you follow that? If X is not an adherent point, that means there exists an open neighborhood U of X so that U intersection A is empty. Call this one. Yeah, very good. Now what is X? X is an adherent point of B, and U is an open neighborhood of X. Therefore, what can you conclude? U intersection B is not empty, right? So let Y belong to this. Now Y belong to B. What is B? Y belong to B. That implies Y is an adherent point. Y is an adherent point of A. Yeah. Now go back. Y is an adherent point. Y also belong to B. Y belong to B, and Y is an adherent point of A. Sorry, Y belong to U. See that? Y belong to U intersection B, therefore Y belong to U, and Y is an adherent point of A. That means what do I know? This implies U intersection A is not empty. Look at 1 and 2. They are contradictory. Or arithmetic contradiction. So this contradiction shows what? If X is an adherent point of B, it must be in B, right? Therefore, conclude, if X is an adherent point B, then X is in B, that is, B is closed. So A is a subset of B, and B we already saw is a subset of closure, but this is already closed, and A closure is the smallest closure which contains A. Therefore the conclusion is A closure is nothing other than B. So we have a complete description. Do you see that? So we have a concrete description. Okay, A closure, that is closure of A in X, is nothing other than set of adherent points of A in X. That's it. Very beautiful description. And as a side remark, those of you who are learning topology for the first time should ignore the remark which I am going to make. Some of you might already learn the word limit point, which I keep saying it for me, it's a cluster point. Yeah, according to your definition, you will say A closure equal to A union limit points. You understand that? Whereas for me, it is set of adherent points, because any element of A is also an adherent point of A. Therefore, this is the most beautiful. Believe me, this is far superior than the so-called limit point cluster point. Okay, to work with points topology, deal with almost anything with closed set, this is good enough. Right. So pause, review, proceed. So if you notice in our various examples, so let me change the color. So in many of the examples from our list, okay, we have found the set A, we find its adherent points of A. That means we have found the closure A, right? That's it. Okay, so a lot of sets we have looked at, and they have found their closure also. Okay, so go back and review this aspect. Okay, just go back to the last video. just not to be left out, let's look at, I left out two examples there, so let me just do those examples here. Let us take R with ray topology, right? So any non-empty open set is of the form this, other than this, right? Okay, now I want to know what are the, so let us start with A equal to A infinity itself. So I want to know what is A closure. So what do I know? This is same as saying, okay, what are the adherent points of A? Every point of A is going to be an adherent point of A. Therefore, what should I look at is, I have to look at, okay, this is my A, okay, right? So let us look at an X, okay, which is less than or equal to A. I want to know whether it can be an adherent point. You follow that? Okay, so if X is less than or equal to A, is X an adherent point? Okay, so among all those points, I have to collect all this thing, right? That's very easy now. Now, what are the typical open set if X is less than or equal to A? What are the typical open sets? Now you understand the reason why I kept saying typical open neighborhoods of X. So it has to start from any B so that B is less than X, right? They are of the form B infinity where B is less than X. Do you follow that? Right? Yeah, that means since X is less than or equal to A, this is less than B, what does this say? This is A infinity is contained in B infinity. This is your set to U. Okay, typical open neighborhood of X, right? Therefore, U intersection A is A all the time. So it's in particular it's non-empty. Therefore, what is this thing you have concluded? Therefore, every X in R is an adherent point of A infinity. Yeah. Therefore, for every A in A infinity closure, this closure is what? In ray topology, right? Therefore, it's a closure in tau ray topology of A is all of R, right? To make sure that you understand, try to do with N with the topology we have defined earlier topology, okay, exercise, and also do with R with co-countable topology and yet with co-finite topology and N also with this initial topology kind of thing. I don't remember what I called it, but whatever it is, okay. So are you happy? Yes or no? For example, R with VAP topology, 0 as the VAP. We have shown that if I take 0, then its closure is all over. And if I take any A non-zero, then this is already a closed set. Therefore, this is the closure is itself, and so on. And discrete, indiscrete, everywhere you have seen all those things. Okay. So please review, because I define only in terms of adherent point. Now that I have defined closure, you should know, right? So your exercise is go through all the examples in which we identified the adherent points of a set A. And okay, so that we have found A closure, right? Okay, now let's take a break. We will go to something else now. Now we want to see how adherent points behave with respect to that is, okay, how adherent points of a set behave related to continuous maps. What is the question? It's a little vague, right? Let f from x tau, if you want to have x, to y tau y be continuous. Suppose a is a subset of x, right? And suppose x is an adherent point. What is the natural question you should ask now? Yeah, so I have x and this is my a, and this x is an adherent point of a. Next I have y, and this is my f of a, right? I have fx. Okay, I have fx somewhere. I do not know where I have. Okay, fx. So I want to know. What do you think I want to know? Question is fx and adherent point of f of a. Okay, let us go through the proof. Yeah, so to show fx is an adherent point of fa, what should I do? I have to start with an open set, right? Okay, of fx. So let v be an open set of fx, be an open neighborhood of fx. What I have to prove? Does b intersect f of a? This is what I have to prove, right? Now what do I know about f? F is continuous. Therefore what is an, and you have given me an open set B containing fx. So what do I know? I know there exists by continuity of f at x, there is an open neighborhood u of x. So that what happens? F of u is contained in V. Do you agree with that? Yeah. Now what do I know about x? X is an adherent point, right? Go back to, let's look at this is x. Therefore what do I have given? I have given an open set containing u, right? Therefore it has to intersect a. There should be an a. You understand that? So x is an adherent point of a. Therefore there exists a a in u intersection a, because u is an open neighborhood of x and x is an adherent point of this, therefore right? But what does that mean? A belong to this, therefore f of a will belong to f of u, and f of a also will belong to f of u. Do you understand that? A belong to u, therefore f of a belong to f of u, and therefore I know f of a belong to f of u intersection f of a. But what do I know about f of u? That is contained in B. Okay, therefore this is contained in V intersection f of a. F of u is contained in B, therefore f of a, right? You follow that? So I have proved that B intersection f of a is non-empty. Yes. So what is that I have shown? So I start with a subset A and let x be an adherent point. I want to know fx is an adherent point of fa. To prove that, I used to start with an open set neighborhood B of fx, right? Then using this way I found a u using continuity. Now u is an open neighborhood of x is an adherent point of a, therefore I know there is an a common in a in u. But f of u is contained in b, therefore f of a will be in f of u as well as in f of a. But f of u is contained in b, therefore it is going to be this is your b. Therefore this is my f of a. Pause, review, proceed. So what is the question you can ask? So what do you think I have proved? I have proved if f is a continuous function from x to y, and if a is a subset of x and x is an adherent point of a, then fx is an adherent point of fa. Right? So what should be your next question? You want to ask the converse. What is the converse? Let f from x to y be any map. It has the following property. What is the property? Let a be any set and x be an adherent point of a, then I know fx is an adherent point of fa. You follow that? Yeah. Then what do I want to conclude? Is f continuous? Please formulate. As I keep saying, for many people logic may be the problem. Converse. What is the assumption? F from x to y any a map. I am not assuming continuous, right? It has a property. Following property. What is the property? For every subset a of x and for every x adherent point of a in x, fx is an adherent point of fa. Then what do we want to know? Is f continuous on x. Is the question clear? Just go back and try to understand. Let us prove this. I want to prove the converse. So assume that f is not continuous. I want to prove f is continuous at each and every x. To prove that at every x in x, right? Suppose false, then f is not, there exists some x. There exists x in x, so that f is not continuous. Do you understand this? Sure. Right. So if f is not continuous at x, what does it mean? So again, let us look at, I have x, I have y, and this is my x and this is my fx. It's not continuous. What does it mean? That means there exists an open set V containing open neighborhood of fx, and so that what happens? You give me any open set u, right? Then if it's continuous at x, what should I show? You give me an open set, I should find there exists an open set u, open neighborhood u of x, so that f of u is contained in V. That is false. What does that mean? Again, it's logic. That means give me any open set u, open neighborhood u of x, then f of u is not contained in V, right? That means given any open neighborhood u of x, f of u is not contained in V. So a subset is not contained in another set. What does it mean? That means there exists an element, call it x u in u, so that f of x u is not in V. Do you understand that? There exists an element xu. This is a bad element. This is my xu. Okay, it may depend on you. That's why I'm defining like xn, right? I'm defining xu. This is not in you. Do you follow that? Yes or no? Good. Okay. So what have we shown? For every open neighborhood u of x, I have found a point x suffix u so that its image f of xu is not in V. Now what do you think I have to make use of the hypothesis. What is the hypothesis? Okay. For every subset a of x and for every adherent point x of a, f of x is an adherent point of f a. You may remember in one of the earlier lectures I said whenever the hypothesis says for every element something happens, in the proof you have to make a choice of that. Okay, you cannot keep saying every. So I have to make a choice for capital A. You understand? After that I have to make a choice for x, some particular adherent point of A I have to choose. Then I should arrive at a contradiction. Do you understand? You see that? These are the small tricks which I am teaching. Okay. Whenever the hypothesis says for every some element something happen, in the proof you have to make a smart choice of that element to arrive at some contradiction or to conclude the result. Here I want to arrive at a contradiction. Okay. So I have to find a and I have to find an adherent point of that particular set A also. Now look at the way we are done. What do you think the set is? See, you start with x, okay, and for every u open neighborhood of x, okay, I have an xu in u, right? Yeah. Now do you see something? This is the only thing. Okay, this is where the creativity comes. What should be my a? Consider a to be the set of xu where u is an open neighborhood x. For each open neighborhood I have found it, right? This is under set. Yeah. Okay. Now x is an adherent point. Why? Because you start with any open neighborhood, call it G. G is an open neighborhood of x. Then what do I know? There is x suffix G, right? In where? In G, and of course it's in A because A is the collection of all such x sub G. You understand that? What is this x sub G? It's not sub G, vegetable. If you think it's a sub G, then B become vegetables. So that f of x sub G is not in B. You understand that? Okay. Therefore, okay, make sure you understand this. Now we are through. Therefore, x is an adherent point of A. Now I made a special choice of A. I also found one adherent point. With A may have a lot of adherent points. Every xu is also an adherent point of A. But I make a special choice. Okay. Now what? Now I can apply the hypothesis. What does the hypothesis say? By hypothesis, fx is an adherent point. Yes, right? Now V is an open neighborhood of fx, right? Therefore, what should happen? Okay, fx is an adherent point of fa and V is an open. Therefore, this implies fa intersection V is not empty, right? That means there exists an element in A. Any element is of the form some x suffix u, say x suffix u, so that x suffix u belong to A and f of x suffix u, okay, belong to f of a intersection b. In particular, f of xu belong to b. Yes, but how did we choose our fx? Right, we chose our xu in u such that fxu is not in b, but you concluded there is at least one xu such that fxu belong to b. This is a contradiction. Therefore, what have you shown? So f is, why the contradiction arose? We assume x is not continuous at x. Now we have concluded f is continuous at x. Therefore, f is continuous on a. Okay. See, I deliberately did this thing. I should have left it as an exercise for you. But I just wanted you people to be convinced why adherent point is a very beautiful notion, which is not that well understood, and its some distinct cousin, namely the so-called limit point cluster point, is given ivory pedestal. Okay, but this is the most important concept. Learn this, you will see that throughout your life you don't need anything else to deal with closed sets in topology. Okay, but as a law exercise, I'll give this. Suppose x tau is a topological space. Do you remember we have proved for every non-empty open set, okay, u intersection v is non-empty, then we said any real valued continuous function is a constant. Yeah, so we can somewhat generalize this. What is that? So let x tau be such that for every non-empty open sets u and v in tau, u closure intersection v closure is not empty. Then any continuous function f from x to r is a constant. Try it on your own. Okay, the proof is similar to the earlier one. Okay, now you just have to use the following fact. Okay, and before that, before that, do this easy exercise. Okay, this is, suppose this is n plus 1th exercise, this is the nth exercise. Okay, f from x tau x to y tau y continuous, right? A is a subset of x, and this is exactly what you proved earlier, but you may or may not realize. Prove that f of a closure is contained in f of a closure, that is f of closure of a in x is contained in closure in y of f of a. Actually, this I proved more or less imitating the earlier argument. You should please do all these things. Okay, do not become discouraged. Okay, learn these things well, you will see that it's much easier. And if you master the last 2 lectures about adherent points, you will never ever be worried about closed sets. Okay, so far we have seen 3 ways of showing a subset is closed. One is by definition, A is closed if A complement is open. Second one is A is closed if and only if every adherent point of A lies in A. The third thing is if A is a subset of a metric space, then A is closed if and only for every sequence AN in A. If AN converges to X, that limit X must be in A. Right? There is a fourth powerful characterization. Okay, I should have done it Now I do not know, I think the time is up, so we will do it in the next lecture. And let me repeat, do not worry about remembering anything. Yeah? Just go through the argument, revise it, revise twice or thrice. Your whole focus should be on understanding and trying to think along with me. Do that. If you want, forget it. Actually, you won't forget it. You'll remember it very well. And then later, all the topology concepts will become much easier. Okay. And another thing, if your logic is bad, please go through for some foundation lectures also. Okay. That's it. Okay. Have a good. I hope all of you enjoyed. For some of you, it might have been tough going, but please revise it. Okay. Okay. Take care. Stay safe. We'll meet again.